So today we'll be looking at the PV diagram that contains isothermic curves that maintain a constant temperature. And we're going to be examining the relationship between pressure here in the y-axis and specific volume in the x-axis. And we're going to be using this critical point C here to come up with equations that we can then use to find A and B parameters for the van der Waals equation of state. So if we look at our critical point here, we can see that the tangent line at that point is going to be 0. So the slope of that tangent line is going to be 0, which means that our first derivative at the critical point is going to be 0. And then also, if you look at the curve here at the critical point, curve of temperature, we can tell that it's going concave up to then concave down. So that means that our critical point C is also an inflection point. So if you remember from calculus, that means that the second derivative at our critical point is going to be equal to 0. So we're going to be able to use these parameters, the derivatives, first and second derivatives at our critical point, to be able to derive equations to come up with our A and B parameters at our inflection point. So this is going to be our van der Waals equation of state that we're going to be looking at with our A and B values in there. Before we take the derivatives of this equation, I just want to explain a little bit like what our variables mean in this equation. So we have P on the left side, which is going to be pressure, our R value, which is just a constant, T, which is going to be our temperature at the critical point, V is going to be our specific volume at the critical point. And to explain what B and A are is going to be really important, so that way we know, you have an idea of like what we're kind of trying to get at in this case. So B is going to be our excluded volume. So if we have some container with a gas in it and we treat it as an ideal gas, we usually neglect the fact that the gas particles have some kind of volume. They take up some volume, and it's not going to be very much, but B is going to account for that excluded volume that we don't usually take into account of. And then our A parameter is going to be taking into account another really important factor when we're dealing with gases. So if we're looking at our closed container again, the gas particles in that container do have some attractive forces. They do interact with one another. So it's going to take into account that small amount of pressure that is decreased when these particles are being slightly attracted to each other and pushing less on the container walls. So now we're going to go ahead and take the first and second derivatives of our van der Waals equation of state. And again, we can take these derivatives because our critical point has a slope of tangent equal to 0 and because it's an inflection point. So if we go ahead and do our first derivative here, it's going to be the derivative of pressure with respect to volume, and we're using our volume at the critical volume and temperature at the critical temperature. So if we take our derivative, it's going to look like negative R at the critical temperature divided by our V minus B, volume minus our B value, squared, minus 2A over B cubed. And then again, this is going to be equal to 0 because our slope of tangent equals 0. So just to make this simpler and get rid of the negatives, I'm going to set them equal to each other and get rid of our 0 here. So this is going to be one of the equations that we're going to be using. So now if we take the second derivative, and again, we're using our critical volume. Oops. and critical temperature. So now we're going to have 2R at our critical temperature divided by our volume minus our excluded volume. That's going to be cubed now. Oops, not equals. It's going to be adding now. I'm sorry. Subtracting again still. And we're going to have 6A because of our 3 times our 2 divided by our specific volume to the 4th. And again, it's going to be equal to 0. And again, just to like make it look a little simpler, I'm going to set them equal to each other and get rid of our 0. So this is going to be the second equation we'll be using to find our A and B parameters. So if you notice in these two derivatives here, we have all alike terms with our R value, critical temperature, and critical volume. I'm going to add the critical. I forgot to put that in for volume. So what we're going to be able to do actually is divide out the second derivative by the first derivative to simplify this a little bit and make it easier to find parameters for A and B. So now we're going to go ahead and divide our first equation by our second equation. So to do that, we're basically just multiplying by the inverse of our second equation to the first equation. So what that's going to look like, so we're going to take our inverse of our second equation, which is going to be VC minus B cubed over 2RTC, sorry. And we're going to be multiplying that by our first derivative here. And so you can see that our VC minus B's are going to cancel and leave us with 1 VC minus B in the numerator. And our RTCs are going to cancel, so we're left with a 2 in the denominator. So now looking at the right side of our equation, we have the inverse of our second derivative, which is going to be VC to the 4th over 6A. And we're multiplying that by our first derivative, 2A over our critical volume cubed. And you can see our VCs are going to cancel, and we're left with 1 VC in the numerator. And our A's are going to cancel, and 2 divided by 6 is going to leave us with a 3, sorry, in our denominator. So now you can see that we've eliminated many terms here, and we are left with just our B value and critical volume. So we can actually go ahead and solve for B here to get our equation for B. So we'll do that by just doing some basic algebra, cross multiplying. So we have VC minus B times 3, 2VC, and divide out the 3. So then we get 2VC over 3. And to get B alone here, we'll have B equal to our critical volume minus 2 times the critical volume over 3. We can even simplify this a little bit further and say that B is equal to VC over 3. So that's going to be our parameter for our equation for B. So now that we have our equation for B, we can use that to plug it back into one of our derivative equations to solve for A, which is the next equation that we want to get at. So I'm going to use the first derivative, make it simpler for us. Anywhere we see B, we're just going to plug in VC over 3. So we'll have R at our critical temperature over VC minus VC over 3, but I'm just going to simplify that to 2VC over 3 squared equals 2A over VC cubed. And when we distribute out the 2VC over 3 squared, we'll have 4VC squared over 9. So I'm going to go ahead and simplify that a little bit and say 9 RTC over 4 BC squared equal to 2A over BC cubed. So now we can just cross multiply and solve for our A value. So we'll have 9 RTC equal RTC BC cubed equals 8 BC squared A. And we'll just divide by 8 BC squared. Our VCs are going to cancel and leave us with 1 VC. So we'll have A equals 9/8 RTC BC. So now we have found both of our A and B parameters for our van der Waals equation of state using our critical point of a PV diagram. So now that we've determined expressions for A and B parameters of our van der Waals equation of state, we can use these parameters to determine the compressibility factor of any substance at its critical temperature. So if we're looking at an ideal gas here, the equation for that is going to be Z equals our pressure times our specific volume over R times temperature. And Z is the compressibility factor. So for an ideal gas, Z is going to be 1, but since we have our A and B parameters, we can actually plug these values, these expressions in for A and B to then determine the compressibility factor for any substance at its critical point. So we're going to go ahead and do that. So we have pressure equals RT over V minus VC over 3, but I'm going to simplify that to be 2VC over 3. And then our A parameter here, we have 9 RTC VC over 8 VC squared. So now I'm just going to simplify this a little bit further so that we have 3 RTC over 2 VC minus, and then our VC and VC squared is going to cancel out, so we're left with 9 RTC over 8 VC. So now we can find a common denominator and simplify this even further. So that would look like multiplying this left side here by 4 to get it to be 8 VC. So we'll have 12 RTC minus 9 RTC all over 8 VC. So then we can simplify that further. Our 12 RTC minus 9 RTC, we're going to be left with 3 RTC over 8 VC. So now that we have our simplified expression here, we're still trying to get at our Z value, which is the compressibility factor. So if you can see, we have a lot of like terms here. So maybe if we plug in our P for our P up in this expression up here, we can get some cancellations and find our compressibility factor Z. So we'll have Z is equal to 3 RTC over 8 VC multiplied by our VC divided by R times our critical temperature. So if you can see here, our VCs are going to cancel, and then our RTCs are going to cancel. So then we're left with Z equals 3 over 8. And that is actually going to be our compressibility factor for any substance at its critical temperature. So we were able to derive this from using the PV diagram to derive expressions for A and B parameters from van der Waals equation of state based on the critical point. Because they're based on the critical point, we can actually use those expressions to find the compressibility factor of any substance at its critical point. And this is okay to do because substances exhibit similar behaviors past the critical point, where liquid and vapor phases are so indistinguishable that it can be applied to any substance.